All right, so this is insertion sort now. And insertion sort is kind of unique compared to selection sort and bubble sort in that our sorted and unsorted lists, this in the sorted list in bubble sort and selection sort has been absolute. We don't need to, it has been absolutely the sorted list. It has been part of the final sorted list without any differences. Insertion sort sort of relaxes that requirement. So if I have my data, 30, 50, 30, 60, 40, 20. Just like selection sort, we're going to build a sorted list over here. But it's not the final sorted list. When we say sorted, we just mean that we're going to guarantee that the elements are in increasing order. But we could, in our unsorted list, have like the number 1. Oop, my pen died. Oh, now it's back. In our unsorted list, we could have like the number 10, but our sorted list, it could be like 20, 30, 50. So this wouldn't be the final sorted list, but it's sorted in the sense that it's increasing. Whereas in selection sort and bubble sort, our sorted lists are not going to change. They're only going to be added on to. So the way that insertion sort works is instead of, finding the best element, I mean, we just sort of take the current element and we figure out where it should go. So starting at 50, well, we treat it just like a list of 1. So 50 is in a list of 1, it's sorted. So we can start there. So we would have like 50, 30, 60, 40, 20. And then we would move on to 30. Now the idea is that we want to insert 30 into our sorted list. And so, well, 50 is less than 30, so we would want to swap 50 and 30. So then we'd have like 30, 50, 60, 40, 20. And once again, now we're looking at 60. 60, it's greater than 50. And because this whole half of the list is sorted, we know it's not going to be, it's going to be greater than every element before 50 as well. So we can just sort of swap it with itself or just leave it where it is. 30, 50, 60, 40, 20. Now, when we get to 40 here, well, we gotta insert it here. So we say 40 is less than 60, so we can swap it. And we got to continue moving it along. It's well, it's less than 50, so we can swap it. And so then when we look at 30, 40 is greater than 30. So we know that that's sort of going to be its final position in the array because everything to the left of 30 has to be less than it. In this case, there's nothing left of 30, but in general, we're talking. And so and so now that's our sorted list. And finally, now we're looking at 20. And yeah, we got to swap 20 all the way to the back. And so we would look at, 20 and 60 and say, okay, well, 60 is greater, so swap. 30, 40, 50, 20, 60. And then we would look at 50. 50 is greater, so we got to swap. Look here, say, okay, 30, 20, 40, 50, 60. And you can sort of see, I was talking about with selection sort earlier, we only had to do like on the order of n swaps, where n is the size of the list. Whereas in insertion sort, we might have to do n swaps for every element, so n squared total. 20, 30, 40, 50, 60, and now we're sorted. And so the question we might ask is, like, why do we even have insertion sort? And sort of, here's the answer I want you to sort of think about. Suppose I have like some almost sorted data. Suppose I have like 20, 10, 30, 40, 50. So in selection sort, I would pick the minimum, which would be, I'd pick 10, but I would have to compare 10 to 30, 40, and 50. I'd have to compare it to the whole array, and then I would get that. And then I would go to 20, and I would have to pick the minimum of all the remaining data. So I would be comparing 20 to all of this data, even though it's already almost sorted. But selection sort doesn't know that. But if we did it with insertion sort, start with 20, so that sort of becomes the sorted part of the array. Then I go on to 10. And I'm just gonna insert 10 into the sorted portion of the array. So I only have to check it with 20, and then 10, 20, 30, 40, 50. And then to check 30, because I know this part of the array is sorted, 10, 20 is sorted, I can compare 30 to 20, say 20 is less than 30, and I know 30 is in the right position. So it's really easy to just continue onward. I just have to check 40 and it's the same deal. And then check 50, same deal again. So I didn't actually have to do really any. I had to do like one comparison for the case where the data was almost sorted. One comparison per element approximately, compared to selection sort where I still had to compare with every other element. And so if I have a really small list that's almost sorted, if I just have some almost sorted data in general, insertion sort works really well. And the reason why I'm talking about this is because the way that sort of modern implementations of sorts work is in like a library. We usually use some sort of top-down or just divide and conquer sort, which is really fast. And so like we can use something like quicksort, and we can get some data really easily with quicksort that sort of looks like this, where there's some variation in these steps. And so this data is almost sorted. I'll do another video about how quicksort works. But if we can get data like this, insertion sort works really well on this. And so what modern implementations do is they use quicksort to get some data like this. And then they use insertion sort to take that almost sorted data and make it like that really quick. So this sort of touches on when we were talking about binary search versus linear search, this hybridization to make really efficient algorithms that y'all noticed when we were comparing the times. So I got a little sidetracked there, but I think we did cover the mechanism that makes insertion sort work. But I think this was hopefully a valuable sort of sidetrack because it's interesting, right? Like it's such a simple task, sort something, and there's like so many different ways that it's done, and like people are constantly hunting to find like the most efficient way to do it. So, good luck, and thanks for watching.